lot of different analysis here, right? A lot of different economic analysis. And to do those economic analysis, we have used a bunch of data, right? The data could be while estimating a fixed capital investment. The data could be to estimate cost of manufacturing. It could be even revenue, right? Now the question is, where do we get all these values from? So some of these, of course, we get from tables. But in reality, all of these are approximations, right? So the problem is that many of the parameters that we are using are actually uncertain. So the question we start asking ourselves is, how do we take this uncertainty into account? Okay? So like for instance, let's consider a very simple case where we are doing an analysis of NPV. Okay? And for simplicity, let's just assume that you start building, the building construction takes basically 0 time. And so the NPV is simply minus land, minus FCIL, minus working capital, and plus, and let's say the cash flow is the same year to year, over 10 years, just for simplicity. Plus cash flow, which of course is going to be revenue minus COM, B minus the taxes, it's T, revenue minus COMB minus FCIL over 10, right? So that's the cash flow, and then it's the same cash flow every year, so 1 plus I is about 10, minus 1 divided by I. 1 plus I is about 10, plus land plus working capital, 1 plus I. Okay? So this should be obvious to everybody. But now the question we are asking ourselves is, what if, let's just pick 2 of these parameters that are most likely going to be uncertain. In reality, everything is uncertain, right? But let's just, for the sake of fun, pick just 2. So let's just say revenue is uncertain, which could very well be, right? Because revenue obviously depends upon the price of what you're selling. The price of what you're selling is going to fluctuate. So revenue is almost certainly going to be uncertain. Also, let's just say COMD is uncertain. And one of the reasons for COMD to be uncertain could be simply the utility costs, right? So those 2 are almost certainly going to be uncertain. But as I'm saying, in reality, everything is uncertain. But just for the sake of this discussion, let's assume those 2 are uncertain. So how do we solve this problem? So that's the topic of discussion today. So now, of course, we have to start asking ourselves, what does it mean when you say something is uncertain? So just something is uncertain, what it means is that, because you know, well, you obviously need to have no certain, it's uncertain, but you have certain amount of knowledge about it, right? Not a precise knowledge, but some knowledge. So that limited knowledge can be expressed as a probability distribution function. So let's say on this axis you have probability, and on this axis you have whatever variable we're trying to calculate the probability of. So let's say in this case is revenue. So although you don't know the precise value of the revenue, you can certainly figure out the lower bounds and upper bounds, right? And those could be based again on historical data. So you likely know the upper and the lower bounds, and in between you'll have some sort of distribution. You may know that, well, one value is more likely, and usually what happens is, if something is random, you usually have what is called a Gaussian distribution. So this is called the probability distribution function. It can essentially have any shape, but frequently its shape looks like Gaussian. Okay, well, in Gaussian, of course, it never goes to 0, it's going to tail off. Okay, so this is the mean. So, does everybody understand the meaning of probability distribution function? It is simply the likelihood of the revenue being of certain value. Okay, so like let's say this is the mean value. So what's the most likely value of the revenue? The mean value, right? All right. So now the question is, and similarly we'll have probability distribution function for revenue, and similarly we'll have one for COMD. Now the question is, how do we factor these distribution functions into our calculation of NPV? Okay, so that's what we're discussing. So really the way to do it is to say that NPV now is uncertain, right? Because of the uncertainty of revenue and the uncertainty in COMD. Okay? So what we do is, we multiply this by the probability distribution function. Actually, you know what? Just for simplicity, let's just say only revenue is uncertain. We'll talk about COMD also here, because I don't want to make things look too complicated. So let's say only revenue is uncertain. So what we do is we multiply it by the probability distribution function of the revenue, and then integrate it on all possibilities, and that becomes our NPV. Okay. So the NPV, as we would define, becomes uncertain because the revenue is uncertain. And so we essentially multiply it by the probability distribution function for revenue, integrate over all R, and that's what makes it the most likely value of the NPV. Does it make sense? Yeah.
So the integral of R, probability of R dr would be what exactly?
Is actually 1. So I'm going to come to that. So probability distribution functions are normally normalized.
Okay.
Their normalized means integral of P, it could be any probability, so in this case it's R, of R, dr, from all range is always going to be 1. Because the idea is that R has to lie somewhere, so the normalized probability has to be 1, right? Just like if you look at a discrete probability, if you add up the probabilities of all different occurrences, the sum has to be 1, right? Yeah.
So you're saying over all the R's?
All the R's, and if you want to be, you can always say R min to R max.
Okay, so we wouldn't be doing that for the NPV, hence we just wouldn't be multiplying it by 1. We'd be doing it over a certain range of R's?
No, because you're not, because we still have an NPV here, right? We have an R here too.
Right.
So integral of PR, dr is 1, but now here it's going to be R times P dr.
Gotcha.
Right? So that's always not going to be 1. In fact, that's what my next question. What is integral of R times the probability of R dr for the same range? What is this?
The average R?
Sorry?
The average R?
Very good. That by definition is what is called the average value of the R, or the most likely value of the R. Okay? So you can denote this to be R bar. Okay? Yeah.
The weird brackets, is that not the same thing? Like,
Yeah, sometimes
I just wanted to make sure.
yeah. Bar, those brackets. Is there a better word for those than weird brackets? Angular brackets? Let's just use bar because I don't want to have to put those weird brackets. Okay. Any questions so far? All right, so in this case, if you look at this analysis, you can see with those two definitions, lift this up. Okay, so now let's look at this NPV bar. So if you do the term by term integration, if you look at the terms that do not have any R, then we can take those common, and when you use this rest of this relationship, you can see that the first term simply remain minus L, minus FCIL, minus WC, and actually let me just write it, times PR, probability of R, PR. I'm not going to put limits because the limits are obvious in all cases, right? So that's all the terms without R. Now let's look at the term with R. You'll have plus R times 1 plus I to the power 10 minus 1 divided by I, 1 plus I to the power 10 times P of R dr, and the rest of terms again don't have any. Actually, I should also include, well, actually, let me include this. Instead of R, let me write R1 minus T. Okay, so I don't have to do those left twice. Right? And of course, rest of the terms again don't have any R. So you have plus integral minus C over B plus B plus times R. Okay? Is that good? It looks complicated, but really it's not. If you think about it, all I'm doing is basically copying the expressions. I'm really not doing anything much with it. Okay, now let's look at the first term. In this first term, everything in these parentheses is not dependent on R, right? So you can just take it out. Yeah? So what you're left with is just PR dr integral. And how much is that? 1. So you see this basically remains exactly the same expression. This expression, this whole 1 minus t times I, 1 plus I squared, this whole thing you can take out. So what you're going to be left with is R times PR dr integral. Now, how much is that? Average R. And the rest of it, of course, again doesn't depend on R, so you can take it out, and this integral is 1. So you can see the most likely value of NPV actually simply becomes the same expression as there. So I'm going to bring it down. Can I bring the board down again? Except that I replace R by R bar, right here.
So are we assuming in this case that Rmin and Rmax actually have definite values? They don't go
Yeah.
from negative infinity to infinity?
There could be actually, it doesn't really matter. No, you will never, likely R will not be negative, right?